so welcome everybody. A way of introduction, my name is Gerald Handler, and I'm an astronomer. And of course, I mean, you all know these memes, what my friends think I do, and what my parents think I do, and what I wish I would did. That actually describes myself pretty well, and what I really do. But then, of course, over the past, like, 2.5, 3 years, we were living in a pandemic. So what I really did during those 2 years was basically sitting at home office, which didn't really go undisturbed. And I think that for many of us, at least for me, it's the first like in-person, real, physical conference for almost 3 years now, and so thank you very much, Manfred, for organizing that, also for being very patient by having to shift the meeting and on. And I'm really happy to be here, and of course giving a talk in person is so much nicer compared to like sitting in front of a screen and pointing towards it and nobody sees it. So, yes. And also by way of introduction, this is my institute, that's the Nicolaus Copernicus Astronomical Center in Warsaw. This square building is where the offices are. This horseshoe kind of building is our hotel where guests live and so on. And my office is even actually in the main building where it's supposed to be. I was already here at the first edition of this conference 3 years ago. That's the group picture. And that's me up there, and I gave a presentation then as well. And now the question to those who were here 3 years ago, and you see yourself on these pictures, what do you remember from my presentation that day? Okay, that's about as much as I do. So no problem whatsoever. I'll just start this presentation with the last couple of slides that I had 3 years ago. And I'll tell you the continuation of that story. And I finished this presentation by showing an email that I got at that time, 3 weeks before, from a colleague in the US who has, together with an amateur astronomer colleague, I'll introduce them in a minute, a very interesting light curve from photometry, and they asked me how can we understand that, and that's this light curve. This is TESS space light curve of this variable star. You see some long-term variability, larger amplitude, and you see some short-term variability superposed on that. And of course, the long-term variability is that of an ellipsoidal variable. I've depicted that here on the bottom, and actually, yes, the advantage of giving talks like physically is that you can actually use models of your stars. And now, of course, the experience that I got through in the pandemic with my home office works really well, because I'm pretty experienced in doing this kind of stuff. So this is my second approximation to an ellipsoidal variable star. Looks pretty similar. So what you have here is a star distorted by a component that's close to it, gravitationally distorted. And of course, as the two stars rotate through their orbit, you get to see different projected surface areas in your line of sight. And that produces some light variations, because you get more light this way, you get less light this way. And of course, also here there's some temperature changes. So usually these stars, unless there's some also effect that the other star illuminates that star, that basically that part is usually cooler and that part is usually hotter. So you also get some kind of color variations. And this is basically the type of object that we had here, and in addition it has pulsations. And what you see And I'll need this model star later again. What you see here is actually that the short period pulsations, they seem to occur only at a deeper light minimum from the ellipsoidal variations. So it looks like that the pulsations in that star are best visible when you look at it like this, and they get less visible here, and they're almost not visible here, right? So the star is oscillating like this, then when it turns around in the orbit, you don't see the oscillations anymore. So it seems like that the star is pulsating only in one hemisphere, which is weird. We haven't seen that before. Okay, and this was actually the very, very last slide that I showed 2 years ago. That's a stack of the light curves. So I have actually chopped up that light curve from the test satellite into different parts that are exactly one orbit long and plotted them on top of each other in a time series. And you can see again here that between orbital phase 0.5, the flat light minimum, there's almost no pulsational variability, whereas here at orbital phase 1, there's larger amplitude variability. You also see that the oscillations don't line up. So they do not occur at the same phase as primary light minimum, but they're always a little bit shifted. And that tells you that these oscillations are not excited by tidal forces, because otherwise they would be aligned. And so these are free oscillations that are modulated by basically the orbital motion of the star. And the question is, how can that happen? That was the status 3 years ago. TESS was still observing that star at the time when I told you about it, so we got more data, and the story continued. I should also say at the time, 3 years ago, I didn't tell you what that star that was. That star is called HD 74423. It's a southern hemisphere star, 8 magnitude or something. The variability was discovered by the person on top. That's Robert Galliano, Dr. Robert Galliano, a retired cardiologist from the US who is an amateur astronomer and looks at interesting phenomena in light curves. And the person on bottom is Professor Saul Rappaport from MIT, who is a retired professor who coordinates actually a group of amateur surveys that check the test data. And whenever Saul doesn't really know how to interpret things that the amateurs send to him, then he asks a couple of his friends. And I'm lucky enough to be in his list of friends that he sometimes asks him. That's how the whole thing actually came about. Okay, we can now separate or distinguish these different kinds of variability. We can decompose that into the long period variations and the short period variations. And here now, in this diagram on top, you see actually only the ellipsoidal light variations with the pulsations removed. So this looks like a normal ellipsoidal variable star. In the middle panel here, you see the run of the pulsation amplitude of the signal over the orbit. And again, what we've seen before is here that close to light, so phase 0.5, the amplitude is almost 0, and it's about 10 times as high at the primary light minimum, and the run of the pulsation phase is also plotted here. And that's an important diagnostic that I will use a little bit in the during the course of this talk.
Gerald,
yes.
Could you go back to the
sure.
What's the way of analysis to separate the pulsation phase and the orbital phase? The normal light phase in the top.
Sure, there's astronomical software for that. The program I was using is called Period of 4, and we're just making commercials again of that, which is, as you say, 0 of 4 is the year in which it was written, so it's available for almost 2 decades. Mm-hmm. You basically transform the light curve into Fourier domain, you determine the frequencies, you make multi-frequency fits to that, and then, of course, you can subtract whatever of the components you have determined.
Okay.
And then you just plot what's left over.
Thank you.
Okay, now, this reminds us of something that Don Kurtz, retired professor from the University of Lancashire, has already figured out 40 years ago in the context of the stars that he was working with. And these are the so-called rapidly oscillating AP stars. These are A-type stars that oscillate rapidly. But what is unusual in those stars is that they are magnetic. And the same way as it also occurs actually in the Earth, the magnetic pole of those stars is misaligned with the rotational pole. So of course, also on the Earth, the geometrical north pole, the magnetic north pole, they are different, and south pole, of course. And what Don has realized that in these stars, that actually the pulsations, it's easier for them to align with the magnetic axis than with the rotation axis. And so if this star rotates, and actually I can again use my stellar model for that, if that rotates, then actually the pulsation axis precesses, and you see the oscillation actually over different aspects over the orbit.
Yes.
So, and what Don has concluded in analogy, oh yes, and of course, I mean, the kind of modulation of the pulsation amplitude and phase depends on what kind of oscillation you have in the star. So for instance, if you had a radial mode, a radial oscillation, nothing would happen. Because you always, I mean, there's no distribution of the pulsation amplitude over the surface. Whereas for others, for non-radial pulsations, for instance, if the star oscillates like this, then you get a modulation of the pulsation amplitude because the oscillations in the two different hemispheres cancel more or less, and depending on how the pulsation points at you and moves away over the orbit or over the rotational cycle of an AP star, creates amplitude modulation and phase modulation. And so you can also even invert the process and figure out what kind of oscillation you have. And Don said that the oscillations of a tidally tilted pulsator we can actually understand by a star where the pulsation axis has been tilted into the orbit. So if that star, usually in a binary system, usually the rotation axis is usually normal to the orbital plane, but the pulsation axis is now here, and the star pulsates like this instead of this. Okay, so we got that figured out actually within a few weeks. We have a cartoon model or an animation of how this would actually look like. So we have two stars orbiting each other, and you see that the star that is the pulsator that pulsates mainly towards the line of sight of the companion star. Okay, that resulted in a paper, even in Nature Astronomy. We are very happy about that. And with that paper, we actually even made it into the Austrian news website, and actually also news in several countries, with a horrible title made by the journalists. So astronomers discover a twinkling star, which is kind of, well, I wasn't very happy with that, I'm still not. However, I mean, that wasn't really the worst deadline on this day. You can see that's the 10th of March 2020. And actually on the same day, there was a different headline also that due to the coronavirus pandemic that was just breaking out, actually, basically on that same day, they started to shut down the country. So in relation to that, it probably wasn't all that bad a headline. Anyway. Now that we found this star, obviously we asked ourselves, I mean, could there be more of these objects? And actually, pretty quickly, Don Kurtz himself found another of those stars. The star is called Sio Carmelo Pardalis. That's actually a pretty bright star. It's a 4th magnitude star in the northern hemisphere. Pretty far north, plus 75, circumpolar here, even. And you see that kind of light curve. You see again that there's less pulsational activity going on in the shallower minima, and there's more pulsational activity going on in the deeper minima. And if you remove the orbital variation, so here on top you have the total light curve, you remove the ellipsoidal variation, you plot what's left over, you can actually see the amplitudes. Note that the scale here is a factor of 5 enhanced. And you can see actually that the pulsational amplitudes are always larger near the deeper light minima. But you can also see that this is not regular. Sometimes the maxima are larger, sometimes they're smaller, and so on and so on and so on. The reason for that is that this is not a single pulsation. These are several pulsations. So, and they interfere with each other. So if you have, for instance, imagine the
non-radial.
Sorry?
Non-radial pulsation.
Yes, yeah, I mean, it's that many that it has to be non-radial, but it doesn't really matter for the sake of what I'm now trying to say, is that basically if you have a sinusoidal variation during to one pulsation, and then you have another one with a slightly different period, sometimes they beat up, so they get high amplitude, sometimes they beat down, you get lower amplitude. This is what we see here, and the beating up always occurs at the time of the ellipsoidal minima. So this again tells us that these oscillations are more focused in one hemisphere of that star. Oops, now again, push the bad button. Okay. Now that's the schematic of that system. It's a little bit different. We again have a pulsator. Do you have a question, Rainer?
Yes. What about the companions? I mean, what's the nature of the companion? I mean, the first case and the second case.
I'll get to that a little bit later.
Okay.
You know, I'm trying to build up like tension.
Sorry.
So that's the second one. But already going to the companion, this is a smaller companion that we had in the simulations before. Obviously, I mean, there's a little bit more knowledge in these animations than I have yet transported to you. We looked further, and one of the amateur astronomers found another of these stars. TIC telephone number. TIC stands for Test Input Catalog. And this is a faint star. This is like 11th magnitudes. But here, the story is different. Because here, we have an eclipsing binary with ellipsoidal variations. And if you look at the light curve, here on top of the light curve, you see the oscillations, whereas here actually, near the light minima, there's almost nothing.
This tiny difference.
Yeah, this tiny difference, but this only appears this tiny because the eclipses are so deep that on the scale it just looks tiny. Yeah. So, and this star is different. Here we've again separated out the run of the pulsation amplitude over the orbit, and you actually see here now that the maximum amplitude here occurs at quadrature, and minimum amplitude here at the light minima. So it seems that basically the pulsations are concentrated here, which makes no sense. But the question, the solution to that is that the pulsations are just of a different type, and the pulsations are. This is a different type of pulsation that is again directed towards and away from the companion. But as you can see here from the animation, I'll probably just run it again, is that if you look at the star in quadrature, they do not cancel out that much. Whereas if you look at the poles, you see a hot and cool part of the surface at the same time, and so they cancel out. So the pulsations are intrinsically actually larger when you look at the line of sight, but since you see both the cool and hot parts of the star, or the extending and receding parts of the star at the same time, and of course your star is only a dot, and you have everything in your aperture, it just cancels out. So this is just a geometrical effect, and there's nothing wrong with our model. Okay. Quick recap, just to see, those three systems are pretty different. So you have two equally sized stars here. We have two different stars here. And then we have an eclipsing binary star here with a different type of pulsation mode. These are the first three, and the tidally tilted or single-sided pulsators that were published. And this answers Reiner's question. This is how the results of our analysis, summarized by paper by Jim Fuller. You see orbital periods are of the order of 1.1 to 1.6 days. The primary stars, they are all about 1.5, 2.5 solar masses. The secondary stars are less massive. Some of them are of similar mass than the primaries. Some are much less massive and much smaller and much cooler. So there's no real systematics. But then, of course, there's only 3 stars. So what can you expect? Right? Okay, now for something completely different. Meanwhile, our team was joined by a young PhD student from MIT, who is working actually with George Ricker, who is the principal investigator of the test space mission, but he also worked with Saul Rappaport, Rahul Jayaraman, and he has also helped with serving the test data for interesting phenomena. And the young gentleman learned really quickly. And it's also him who is now each month when test data come in, he looks for interesting stars. He has automatic routines that dig out stars and then just sends them around. And one of the stars that he sent actually just by accident for us to look at was that one. That is a Super Chandrasekhar binary supernova progenitor. That's something completely different from what we looked before. That's a binary system consisting of a sub-dwarf star and a white dwarf star. These two stars are very close to each other. Here on top, you see again the test light curve for that star. Ellipsoidal variations. Again, just note, it's not noted here, but the orbital period here is 100 minutes. It's a very close compact system. Here's a radial velocity curve that these authors obtained. Note that there's a radial velocity amplitude in excess of 300 kilometers a second within the 100-minute orbital period. So the stars are going around each other really fast, and they're really close. And from the analysis these authors did, also in Nature Astronomy, it turned out that the two stars will at some point merge. When they merge, they will exceed the Chandrasekhar mass, even if you include some masses and so on. So there's an 80% probability that it actually the Chandrasekhar mass is exceeded, and this star will go supernova at some point. Okay. Now Rahul noticed that these authors also found oscillations in that object with periods between 4 and 6 minutes. That's just Fourier amplitude spectra of the star. That's basically showing the amplitude of those oscillations versus period or versus frequency, and there's lots of them. The thing is that the data that these authors had came from an observing mode in TESS that gives one data point every 2 minutes. Okay? And one data point every 2 minutes results in a natural limit that you can only look for periods down to 4 minutes in those data. And the pulsations are between 4 and 6 minutes. So these authors said, okay, now we're careful because there could be problems with the interpretation of those data, because you will have basically a mirror image of these oscillations sitting just at shorter period. It's actually also this kind of aliasing problem that I just mentioned, a different flavor of this aliasing problem that I mentioned before. But now Rahul noticed that after a new 20-second cadence observing mode in TESS was introduced, one can actually analyze the pulsations. And Rahul asked, is that of any interest? And so I looked at the data and I realized this is a lot of interest. Notice already that this frequency spectrum looks very, very regular. There seems to be very similar spacings in here. And the first look actually at the spacings of those dominating peaks already showed me that this is actually the orbital frequency. So I thought, oh, you gotta look at that one. And I looked at that one. And actually it is a tidally tilted pulsator, just of a completely different kind. And for that star, we could identify 31 independent pulsation frequencies. So far, we had 4 pulsation frequencies for one of those delta Scuti main sequence binary systems, 27 of which were actually modulated tidally over the orbit. So this was opening, of course, up completely new doors in the analysis of these stars. And the question, of course, is this now a scientific curiosity, or can you actually make use of that? And of course, the answer is we can make use of that. Of course, in the beginning of the talk, I've promised that these are unique astrophysical laboratories. Somebody said that, everybody says that. Jaroslav, okay. And actually, I hope by the end of the talk, I have convinced you that actually this is true in that case, and these are not just empty phrases. So, what can we do with those stars? Now, Ernst has already dropped the keywords non-radial pulsations, and this is what actually my main speciality also, specialization in astronomy also is. And stars can oscillate in many different ways, and here's just a different a representation. Stellar pulsations can have different surface patterns, and I do not intend that you understand all of them now, within a few minutes. It's just enough for you to know that they are there, and they are different, and they are different oscillations. So that means if you observe many of them, so for instance, if you observe in that star 27, we know immediately this can not all be radial pulsations. Why is that? The reason is that pulsations are basically standing waves in the star. So the star has to go in a resonance, so you have a fundamental pulsation, you have a first overtone, you have a second overtone, and so on. So you have actually distinct period values that a certain pulsation can have. And if you find 27 pulsations in such a star, it's too many that these are all radial. So it's got to be those non-radial pulsations. And we can make use of these non-radial pulsations in the sense that these different oscillations, they obviously, because they're waves inside the star, they go into a certain depth of the star and then reflect on the surface again. So they reflect inside and they reflect outside, and they make a standing pattern in that star. And basically the star's oscillations sound like a musical instrument. And if you listen to that musical instrument, you can actually figure out how the musical instrument is built. Or another analogy, if you listen to a flute and listen to an alphorn or whatever, because of the frequency of the tone the two instruments give, you know immediately that the flute, because it has a higher frequency, is smaller, and the alphorn is longer, because it has this low tone. We can do similar things with stars, and we can also learn other things about the stellar interior with that. It works a little bit like tomography, or ultrasonic sounding. Different kind of stars produce different kind of oscillation systems. oscillation spectra. So subgiants, red giants, they are different, for instance, in frequency. Red and blue giants, they have different ways of driving, different types of oscillation, different light curves, different frequencies. And what we're trying to do is to use the stellar signal, revert that, and then figure out how the stars are built up in the interior, similar to ultrasonic sounding. So going back to that, we can figure out what kind of oscillation modes we're dealing with. And now we have the advantage with these tidally tilted pulsators that they're in binaries, and they are locked in the orbital plane. So again, if we had a single star that's oscillating, so you always see it from the same side, nothing's happening. But now, if the star is in the orbit, and you've already seen that also in our animations, and it's being carried around, you see actually the oscillations from all possible aspects. Turns around. It also depends, for instance, on how the orbital plane is tilted. So you get a different modulation pattern depending on actually how the pulsation axis of the star is tilted and how the orbital plane is tilted. People have realized that 17 years ago. My great Steve Kavala and another graduate student from there, from Iowa State University, and they have actually made numerical simulations of how these oscillations should behave exactly in that case. So basically, the way to understand, to revert our observations into the underlying geometry of those stars has already been there. And this is, for instance, for a given kind of oscillations, depending on the geometrical, on the angle of the pulsation axis and the angle of the orbital axis, how the pulsation amplitude or the pulsational signal will vary over the orbit. So now we just need to invert that. But even better, I mean, of course, our stars are in binaries. So we have, and if we're really lucky, they're in eclipsing binaries. So we can, of course, for those stars, determine the orbital inclination or get constraints on the orbital inclination. So we can throw out lots of these hypotheses. And of course, we can work under the assumption that the pulsation axis is within the orbital plane. So we basically have, from the observations, only a very small possible subset of those that are possible at all. And therefore, this makes our life comparatively easy. Different oscillation mode, just to see what kind of wild behavior you would be getting. Our diagrams that show actually the run of the pulsation amplitude over the orbit and the pulsation phase over the orbit actually can be inverted in what kind of underlying oscillation mode you have. And this is an example for this pulsating subdwarf white dwarf binary. A couple of the 27 oscillations that we found inverted into or mapped into what kind of pulsation modes we have. So basically, we know for that star what kind of oscillations we see. We have these modes identified and what frequencies there are and so on. It can be modeled in detail. Which is, if you remember the date of the publication of that star, it was 1st of April this year. We're not done yet, but we know we can do it, so Jim Fuller is working on it. Now, here we are on a spectroscopy symposium. So why is this guy talking about photometry and basic astrophysics and all these kind of things? Is your present speaker at the wrong conference maybe? Has he gotten lost or has he not understood the topic of the conference? He has, but you have to read the small print, you know? I mean, in astrospectroscopy we gather, astrophotometry, and astrophysics. And what I've done is I've actually just reverted the whole thing and told you so far about astrophotometry and astrophysics, but I haven't told you about the spectroscopic part yet, although it was hidden already in there. So, for instance, Rainer asked, what about those companions? How do we know what the companions are? The answer is spectroscopy. So, of course, we use the help of spectroscopy to learn a little bit more about those stars. And for instance, that first star we discovered, we asked for telescope time at the South African Large Telescope immediately, and we got radio velocity curves. And these are the radio velocity curves. Of course, from the photometry, we already know the orbital period, so we can phase the radio velocities immediately, and we could, for a given assumed inclination, derive the masses. For instance, and then, of course, together with light curve modeling, with the ellipsoidal variations, with the radio velocities, we could get the parameters of the systems. We can see here that basically we have two stars of equal mass. For the other star, COCAM, we were lucky because, as I said, that's a fourth magnitude northern hemisphere star. People had actually pretty recently gotten a radio velocity curve for that star and published it. And so here, that the secondary star could not be detected, but the primary star radio velocity curve could be inferred, and that's the radio velocity curve. And so we could also determine the parameters of the system, also together with the modeling of the ellipsoidal light variations. An interesting question that also spectroscopy can help us with is actually, and that's discussed in the literature also, where do actually the pulsations sit? Because, I mean, from the photometry itself, it is not 100% clear, it's not unambiguous at which hemisphere of the star the pulsations sit. They could sit either here, or they could sit either here. Problem with the ellipsoidal, or one difficulty with the ellipsoidal variables is, of course, if your star is fainter but hot, and you have a primary pulsating star, then the hot star could shine on that part of that star and actually heat it up. And then in the ellipsoidal light variation, you actually get the shallower light minimum here, where with a cool companion, you would get the deeper light, the shallower light minimum here. And here now you get, with a hot companion, you get the deeper light minimum. And that, of course, also gives an ambiguity, because from the photometric characteristic of the ellipsoidal variations alone, you cannot really separate, you cannot really say is that really the part of the star that's facing the companion, or is it the part of the star that facing away from the companion. And so people have made actually model calculations for solar light oscillations of tidally distorted stars. And what happens there is that the oscillations, these rapid oscillations, like in solar-like stars, they actually tend to die out here at the part that's facing the companion. They can resonate here, but here they just don't feel enough resistance from the stellar surface that they're just dying out, and the oscillations are actually concentrated in that part of the star that's facing away from the companion. Okay. However, the pulsations that we have in our star are not the same kind of pulsations. These are more global pulsations. And so our colleague Jim Fuller, who does the theory, I'm not going to explain those plots, but that's what he did, has said that no, for our stars, actually pulsations will concentrate here because the star is more extended here. It's fluffier, it's easier. The pulsations can penetrate a little bit closer to the surface. We see them better here. So, who's right? Who's right? Okay. The answer is, of course, the star is right. The star knows what it does. We have to figure it out. There's a simple way to do that, and then again, that is spectroscopy. Because imagine you have the star sitting, or the secondary star sitting here, the pulsating star sitting here. Now say the pulsations are here. You have in this position, you have basically zero radial velocity because the pulsating star is moving perpendicular to a line of sight. But then the system starts to rotate, the star starts to move towards you. Radial velocity gets negative. It's more negative and so on. Okay? Now, if the pulsations were sitting here, you don't see any pulsations here, and then when it gets more negative, you get basically the if you have the pulsation maximum at the receding line of the orbit, you can say that the oscillations are sitting here. So basically, there's a 180-degree difference in the phase of the maximum pulsation amplitude and maximum radial velocity that you're measuring. And so we need the spectroscopy to see, to say where actually the pulsations are sitting. For our first star, where we had two similar components, the problem is that each of them could be the pulsating star. So the pulsation could sit on either. We could determine, okay, the pulsation sits on one side, but it could be the other side, and it sits on the other side. So that doesn't really help. So
could both pulsate? I mean,
there's only one pulsation mode, so it's only one star that pulsates.
Really?
Strangely enough,
Yeah.
although both could theoretically, but there's only one. But we don't know which one. There's another spectroscopic method, basically because, as you see, I mean, the radial velocity amplitude is large, so the lines, the spectral lines separate at some point. So you could actually look, when the spectral lines are separated, which one shows line profile variations due to pulsation. So we could figure this out, but that's pretty difficult. We'll leave it for the time being for other people to do it. But here, for that star, and yeah, I should say, basically we spent, 8 months to get this radial velocity curve after the discovery of that star. We couldn't figure out where the pulsation sits, and we were really disappointed. Then we found the second star that has a published radial velocity curve, a pulsating component and a non-pulsating component, and we could line up the photometric light curve or the ellipsoidal variation with the radial velocity curve, and I checked again in our emails. We figured out within 15 hours that it's actually that the star actually rotates towards the companion, that one. But there's only one star of two I could figure it out so far, but the pulsations are enhanced at one. Another thing that I just said, line profile variations due to pulsation. This is also something that spectroscopy can do for us. What's the case here? So if we look here at the left animation, you have a pulsation that is moving around along the stellar equator. Okay. at the phase, for instance, when we see the blue part, let's say the blue part is the part of the star that's coming towards us, and the red part is the part of the star that's moving away from us. The part of the line profile that originates in the blue zone is a little bit blue shifted because it comes towards us. The part of the line profile of the star that's moving away from us is a little bit red shifted. So you get a little bit additional flux actually in one part of the line profile. And the line profile gets distorted. And because of that distortion of the line profile, you can also figure out what kind of oscillation you see here. And this is what's depicted here. So when we see the white line, which is where no pulsation is taking place, in our line of sight, we get the normal line profile. And whereas when we have one hemisphere dominating, we get this distortion of the line profile. And so this is another way of how spectroscopy can actually help us figure out the pulsations. And I should say that yesterday, within 15 minutes, we learned how a Pulsators line profile originates. Now, within 1 minute, we learned how pulsational line profiles originate, which tells you how much easier that stuff is. So, in the end, so I mean, this is about enigmatic spectroscopy and so on, and now I'm opening a little bit our treasure trove. I've told you about 4 of such tidally tilted single-sided pulsators so far. And we have, of course, not stopped working with one of those. We just haven't published them yet. So here is an overview of our treasure trove, maybe Pandora's box, because perhaps we'll find one or more kind of strange objects in there. Stars that, 9 stars that I would call new tidally tilted pulsators that we haven't published yet. Just some basic information. Most of them are unfortunately pretty faint. For 2 of them, we have already gotten spectroscopy from salt. For 1 of them, there is literature spectroscopy, but it's insufficient. It's a 6th magnitude star in the northern hemisphere, Hercules. So that one is a pretty good bright object for spectroscopy. And then we have candidate stars that look a little bit like those tidally tilted pulsators. And 1 bright object is also among them, also in the northern hemisphere. And so this is that object that is in need of spectroscopy. On top is the orbital light curve. And it's an ellipsoidal variation, and you see tiny little eclipses, so it's just grazing eclipses in that system. And you see the run of the pulsation amplitude over the orbit, so you see the maximum actually again here at the deeper light minimum, and you see a second maximum near the flatter light minimum, so that gives you the type of the mode. Again, a 100, or actually 360 degree phase jump, so that's actually not physical, it's just phase ambiguity. So we have, and we have a second mode that looks slightly different. It's probably higher, almost no phase variations, so I think from the terms of non-radial pulsation, it's probably an L equals 2, M equals 1. Anyways, this star is called 32 Hercules. It's 690 magnitude. It's an orbital period of 3.394306 very accurate days. Problem with that for us is that these observations were taken in 2005, 2006. The photometry we have was taken in 2020. Yeah, second year of the test mission. And the problem is that even though the pulsation period from the spectroscopic data is so accurate, the error in it over those almost 15 years break add up sufficiently that we cannot face the radio velocity curve with the photometry unambiguously. So we do not know, for instance, on which side of the star is the pulsation, because we just have an error in the phase extrapolated to our time of observation, which is about 180 degrees. So for that star, for instance, say 8 to 10 spectra, one spectrum each night, so no really high cadence or something, so whenever, because we have these new observations, there will also be, we have asked for and actually been granted the director's discretion time on test for that star for new observations that will be carried out actually pretty soon. I think in August or something. And then with new spectroscopy, we will be able to actually get that system solved. And that's actually, I think, even easy for if you have a reasonably large telescope, I mean at least 30 centimeters, 50 or something, and spectrograph with resolution of, I don't know, above, say, 6,000, that should be pretty easy.
Which lines are
more
interesting?
Usually, this is a mid-A type star, so would look somewhere. I mean, there's always a trade-off, of course, for spectrograph efficiency and also the color of the star and the number of and strength of the stars that are in there. If I'm using professional telescope, I usually look somewhere between H gamma and H beta, because there's lots of metal lines in there that you can use. But if your spectral, or if your detector response or your system response is not that good so far in the blue, then of course some lines, redwatch of H beta can also be found. I usually try to avoid hydrogen lines because there are other complications coming with it, because equivalent with variations, especially if you have a star with a non-equal distribution of surface gravity over the surface, then of course you do get rotational, or you get aspect effects in your line width, especially in the H alpha lines, so in the hydrogen lines. So I don't really recommend those.
Spectral type of this star?
From the top of my head, like A8. And yeah, that's the most promising candidate. I mean, I had another 6 magnitude candidate also in the Northern Hemisphere, but that one, the observing season is just finished, so that one won't be available until like October, November or something. So that's what I can offer you. And the other thing is, we just recently got a grant project funded finally, where we also have involved an automatic search for these kind of variables. So we hope to dig out many more of those, and then of course hoping many bright representatives of those as well. Because I mean, so far our discoveries were just coming from chance discoveries, visual monitoring, scattered amateur searches, and so on and so on. So I hope we can now make the let the machines do the search. That's it. Thank you very much.
A lot of motivation aspects.
So you mean that you need this spectroscopic data very close to this date? So you said you need it until August, or?
See, basically, we can write the publication once we have some spectroscopic data.
Okay.
So
Earlier. Okay.
I can't say anything. So basically, the sooner we have it, the sooner we can do something about it. But you know, the new TESS observations will come. Yeah, TESS usually observes a little bit towards the end of the observing season. That starts in Hercules, which is of course, perfectly observable right now from the Earth. But the test data always come a little bit later. Like the observations will take place in August, so then they will be downloaded like in September, and then once they like get available, it'll be early October, which is usually the end of the observing season.
But it's not necessary to have correlating dates between the test data and the...
Not at all. Not at all, because from the test light curves that we already have, we can predict actually the orbital phases relatively accurately within the short time span that passed from the old test observations to now. And of course, with the new test observations, we get that unambiguously. The problem is just that we cannot span the 15-year gap to the literature data.
How many spectra are enough? This particular random.
Random. Just, well, if random is like 10 spectra within 2 hours, then not. But if like 1 spectra each night, it's perfect.
Exposure times makes sense, and longest?
The pulsations are not that fast for that star, so it can be anything up.
Okay.
Whatever, half an hour or something.
Oh, okay.
Yeah.
And signal to rest?
So you can get good radial velocity, so I guess 100 or something.
You mean you can...
Yeah.
Okay.
Everybody
you.
hungry?